Yeah, so there was the operation that wasn't I guess that was mentioned, but wasn't said explicitly. This is just so one operation that we discussed that if the handles has dimension which is not nearby dimension, so if you have the inequality about indices, then you can move so if you have suppose if you have this two handles, so we suppose that the handle of this form, so that the handle of smaller index is attached to the handle of the handle of the smaller index attached to the handle of the upper index. So this means that you have so here you have a touching sphere, and this attaching sphere, it lends. So this means that attaching sphere length of one handle lands on partly on the other handle. Just this I'm drawing as so this is left flow sphere SL lands on the other handle of the bigger index, and the claim is the following, that if you have this if this index is smaller than the index of this handle, then you have the belt sphere. So here you have a belt sphere, and the attaching sphere just is attached to the boundary of this handle, and sits entirely on the boundary and on the remaining. It goes to the remaining part of variety. So we have argued as follows. So if you look at this attaching sphere and the belt sphere of the other point, so as R sphere, so that they have complementary dimensions, and using so notice that it was used the following, so that why we can move this sphere, L sphere, away from SR sphere, because in the neighborhood of this R sphere, the neighborhood of belt sphere is trivialized. So the neighborhood of belt sphere, belt sphere is trivial. Is trivial. So it is just trivial neighborhood of the belt sphere is trivial. So you can times disk. You can apply, since it is trivial, then you can apply sub the lemma explicitly, and you can prove that just SL can be transversal, and since it has a smaller dimension than dimension of this disk, then you can just avoid the intersection at all. But when you cut out this belt sphere, so if you cut out the belt disc, so that out of the corresponding complementary disc, it becomes the corresponding complementary disc becomes the disc without a point. And so so if it is d lambda and this is dn minus lambda, so that when we cut out this disk, then we get dn minus lambda minus the point, and it is multiplied by the corresponding belt sphere. So you can project it backwards, so you can project this to the belt sphere. Yeah, so we are just since you do not have this point inside the disk, yeah, so this you can project it. Yeah, so you can project this disk to its boundary times the corresponding. Yeah, so this the handle is the boundary times the disk. So you can project this. When you extract the middle point of this disk, you can project to the corresponding attaching sphere times the disk of attachment. And this projection allows you to move your handle outside. So this allows you to slide this piece of the handle downstairs of the floor. And yeah, so this from the viewpoint of the flow, this means that you have to make this trajectory, the corresponding sphere, not intersecting this central belt disk. And if it is not intersecting this belt disk, then it will run. So it will you will use the trajectories that will run down the flow. And also the remaining problem that we didn't discuss is the following, that already if you have two points, two singular points that has with the flow landing on the same variety.
Я цвет не взял.
Ну тут как бы вот как раз для лемма. Для диска. Спасибо большое. Для диска лития, может быть, они понадобятся. So the remaining part is the following. So if you have two, now you have the two points of different indices, it even doesn't matter which indices does they have. But what you know about them, that the landing sphere, the attaching spheres, they do not intersect. They land on the bottom variety, and this trajectory doesn't intersect. So the claim is that you can change the corresponding function such that you can change the corresponding functions gradient. So what data do you have? You have gradient trajectories. In order to reconstruct the Morse function, you have to just integrate this gradient trajectories. But the trick is that when you have gradient trajectories, you can do the following. You can make this flow by multiplying by the function. So you can take the function which has nearby this sphere, it has downstairs, it has one support, and nearby this sphere, it has the other support. Yeah, so you can multiply these points just by the function that increases the speed of the flow of this one and decreases the speed of the flow of just surrounded around this sphere. And this will tell you that since the speed of the flow is changed, this will interchange the level of these points in terms of the Morse function. So that's why just you can think of so from topological point of view, if you know that just these bottoms are not attached to each other, it is already for topological purposes. It's enough, but if you want to have this beautiful picture when the trajectory is when the just more singular points are on their own levels, of the then you have to multiply by the function that increases the speed of the flow. And the remaining part is now to understand what happens with this intersection, how to kill the intersection. So how to kill algebraic this intersection corresponding. So suppose you have two handles of nearby indices. So how to kill algebraic intersection? Zero intersection. So this means that just on our handle, you have now this you have now this R sphere, and you have a touching sphere. And they are of complementary dimensions, so they have complementary dimensions. They have transversal intersection, and but the problem is that it is not algebraically transversal, so one just curve can pass something like this. Yeah? So there is the sum of pluses and minuses, and the idea is to first of all to understand the following. So you just have to take this plus intersection and minus intersection, and you want to connect. So you have one variety, which is just a variety P, and you want to, it intersects, so you have the complementary variety, that variety Q, so that intersects variety P in these 2 points, and but I want to give a little bit more dimension here. So what we do? So we want to do the following thing. So we take these points and connect. So we want to cancel that. So we take these points and connect them by paths. Yeah? So of course, so during, if you look at these paths, you can think that just this path is not intersecting. So this path that is connecting. So one path belongs to the variety P, and the other belongs to variety entirely belongs to variety Q. So here you have so just P1 and X1 and X2 will be this X and Y. This will be the corresponding points. And so you have a path that connects these 2 points along one variety and the other. So of course you can think that this path is not self-intersecting by the other, and you want to do the following. So you so it's, these 2 paths. So our variety is simply connected, and moreover, you are throwing the sphere of sufficiently high codimension and the other sphere of sufficiently high codimension. This is because we have get rid of 0 and 1 handles. And then you just this 2 paths bounce a disk. And our variety, after throwing away spheres, it remains simply connected. So you are you can just put the disk that bounds these 2 paths. So what you want to do is to just move. You want to. You want to move your variety P along your move it out along your intersection. Yeah, so if you have just if you look at one-dimensional picture, yeah, so you have intersection of P and so P is here and Q is this just interval connecting these points. So you want to do the following. You want to move you want to draw a pole along in P. Yeah, so you want to draw a pole along this path. Yeah, so that so this means that you want to take P and to move it. Yeah, so just like I put the fingers and press this tongue out of this sheet. Yeah. So just I want to press to press P along our disk outside such that it won't touch our variety Q. Yeah. So you just put your hand just from this side. Yeah. And the idea is that you can do it via the disk. And what you really need to make this work. Yeah, so in order to make this work, yeah, so you have the corresponding so in order to do this, you want to introduce the coordinate system. Yeah? So the coordinate system in these points of the intersection, you have canonical coordinate systems that comes from tangent planes of the varieties. Yes, so this is here you have a tangent plane to P. And you have the corresponding tangent direction to Q. And here again you have to when you move along this path. So what you want to do is to make a splitting. Yeah? So you have notice that without loss of generality, you can so you have two transversal varieties that are intersecting in these 2 points, and you may introduce the metric in such a way that this, I mean, locally in one neighborhood, if you have 2 subspaces, you can introduce the metric, complementary subspaces. You can introduce the metric such that the spaces become orthogonal, of course. Yeah? Just take the corresponding, take any basis that makes you this basis orthogonal, and just you can introduce the metric in such a way that this and this spaces tangent planes will be corresponding tangent planes will be orthogonal. And how you want to press your variety P? You want to press it along the disk. You want to start pressing it along the disk. And in order to do it, you have to be able to split, to press your. So if you want to just draw the tongue, yes, so you have to press your variety just upstairs and downstairs. You have to press it along your path here, and you should press it along the path that goes goes along Q. So you want to press your variety along this disk in one direction, and this corresponds to the following. So you have to be able to decompose, to split your tangent space into the direct sum of P and complementary tangent space. So you have, so here you have you want to free this part of the disk. So you have to be able to split your tangent space in the direction corresponding to the. So here in the tangent space, you have it decomposed this into the sum of the corresponding tangent space to this. Tangent space to the curve. Passing through P, so tangent space to gamma P. It is one-dimensional, and the corresponding complementary part, the normal tangents, normal space to the curve in T of P, and also. So you have this kind of decomposition. Then you want to press your variety just along this tongue. So you want to press it in the direction of the normal bundle of T of P. And when you go just along this tongue and stop at this bottom. So here you have TP, and you have here along this bottom there is a normal direction, and here normal direction also normal direction. It is just normal direction to the so this TP. This part corresponds to TP. It corresponds to the normal direction. So I want to extend. So I have this tangent bundle, and I want to extend somehow this tangent bundle through this path. So to put it. So I want to have this to just I want to extend this tangent bundle along this corresponding path. This tangent bundle can be, when you are going along the variety P, you take the corresponding normal bundle to the normal bundle of curve. But then when you when you go to this specific point, this tangent space is it is still tangent space to P, but you want to characterize it in terms of path corresponding to TQ, yeah, so to the other variety. But since they were transversal, this TP becomes a normal bundle. But you have to still specify what means that it is a normal bundle, so that it is now just TP becomes so TP what becomes in the tangent space of Y, yeah, so to the whole variety M becomes normal bundle to variety Q, normal bundle to variety Q. And I want to explain what does it mean. This notice that TP was orthogonal to gamma P. So here I want to express it, this component in order that it is related with the corresponding bundle of the disk. But here on the disk, so you have the tangent space in Q to the disk, and this tangent space is decomposed into the curve gamma, so tangent to the curve of gamma P and gamma Q. Yeah? And so this just let me draw this. So here you have direction here what? Here you have gamma P, T of gamma P, and here you have the direction T of gamma P, and here you have the tangent space along Q. And now this tangent space to gamma P, when you are looking at this from the, when you start going along this curve, this tangent space play a role of the normal bundle of in the disk to the curve gamma Q. So the corresponding just the part T of gamma P changes to T of gamma Q to the normal part of T of gamma Q in the disk. Yeah, so you are taking the normal direction in the tangent space of the disk. Yeah, so in normal direction in the tangent space of the disk. And the corresponding, so this part, so that correspond to TP, this is just, it becomes just the normal part to tangent space of Q. Yeah? So this with just with the corresponding curve gamma, this Yeah, so the tangent space of Q is, yeah, so you have normal space now to Q, and the normal space, you can look at the normal space to Q, and this is yeah, so modular the so you have to take normal space to Q and take it modular this corresponding direction. The normal, so the disk that gives you the normal direction. Yes, so you have the tangent space to the disk gives you normal. Looking at it in the boundary gives you normal direction to the corresponding normal direction. So you are looking at normal direction modular. So the so orthogonal complement, orthogonal to the normal direction of to the normal bundle of Q to the normal direction of gamma Q to the disk. Just in the tangent space of the disk along gamma Q you have normal direction. So you take in the normal direction to the variety Q you have to take this orthocomplement. And this gives you the choice of the bundle that is consistent of just going around the loop. Yeah? So this gives you, so this gives a bundle which is continuous along the loop. So which is continuous along the loop. So notice that it just this I mean it is only continuous. It is combined in so it just it was constructed almost by hand. I just took the tangent space that is normal to this curve here, and I looked at so I have matched it via taking orthocomplements in such a way that I could express it through the normal bundle to the second variety Q. And via the, so I took information from the normal direction of the disk, so I cancelled one, I cancelled one direction which is tangent to the disk along this normal bundle to Q. And this allows you to decompose your variety. So this gives you the bundle along this disk. And now you do the following trick. You move. You have the splitting. Yes. So what we get so far, we have along the disk we got a splitting of the corresponding vector bundles. Yes. So you can just using the splitting. In the direction which is just tangent. So this tells you how to move along this just tangent space. So you want to do the following. So you want now to take your variety P and to move it gradually. So to move it along the disk, along the direction of the disk, and to lift it in the direction of TP. And in order to do it, you have to just, so looking radial. So you have the so you want to change the coordinates. Yeah, so in the following way. So you just you have this kind of line in the path. Yeah. So you have the path gamma here, and this is a piece corresponding to the piece inside the variety P. And you want to draw a tongue out of this piece, yeah? So this means that you want to, if you want to go inside this direction, so you want to change the coordinates somehow. You want to change this coordinate along this path. Yeah, so with just you want to just so you had the coordinate corresponding to P bot. This is the coordinate corresponding to this direction, and the coordinate to corresponding to gamma. And you using this splitting, you want to lift one going along the tongue. Yeah, so this in this direction. You want to keep so the coordinate of this that you go in this direction. Yeah, so that each. So you want actually to lift this stripe to the tongue. Yeah, so that just you want to just lift it to this half of the sphere. And in order to do it, you have to just be able to split the split the directions of TP and this direction along the curve along all the disk. So this means that you want to split the just in terms of the disk. This means that we want to, in terms to draw the graph of this function, this way we want to split the tangent space, to the whole variety. So you want to find the subspace corresponding to TP bot. Yeah, so this we had this line bundle on this part of the tongue. We have extended so the corresponding normal bundle that we call n gamma q bot along this tongue, and we want to extend it. So we want to have the coordinate system along all the disks, and so we can just do this to raise this tongue as the function. Yeah. So you want to have this splitting of the coordinate system along the disk, and in order to do this, you have to just to have this splitting of this kind of the just of this part of the bundle. And this corresponds to the following. So you have the splitting is just saying that you have the corresponding k-dimensional subspace, where k is dimension of this just orthogonal complement everywhere. So you have this kind of some k-dimensional subspace in the tangent space of W everywhere along the disk. Yeah, so in the tangent space of the disk, you have to have this tangent space of W. But you know that along the loop, you have already constructed this k-dimensional subspace. So this means that in Grassmannian, so this k-dimensional subspace, they are classified by real Grassmannians. So you have Grassmannian of k-dimensional subspace in the corresponding tangent space of W. On the disk you can trivialize it because it is tangent space, yeah? So it is a bundle. But you do not know that it is a bundle, so you have constructed only the bundle on the boundary of your disk. I mean this orthocomplement to the bundle. So you want to extend this bundle to the whole Grossmanian. So want to extend. So this bundle, so T of both of gamma P and n both of gamma Q. So this bundles that we constructed gives a loop. Give a loop in Grossmanian. And the possibility of extending this loop to the whole, so this loop actually bounds the disk. So the possibility, since this bundle is trivialized over the disk, then we can think of this as the loop inside Grossmanian. So if it is and if you can if you can extend this bundle to the disk, so the question to extend the problem of extending the bundle to the disk is equivalent to prove that you can that in this Grossmanian the loop is contractible. Yes, so that in the Grossmanian the loop boundary loop of the disk is contractible. And then the trick is the following, so you calculate explicitly the fundamental group of Grossmanian, and it corresponds to the it is just Z mod 2Z. And this of course should be related with the orientation, so you just take the corresponding, you look along the loop, you pick up a basis here, you start moving your trivialization along the loop in this direction and in this direction, and you have to compare the orientation of the corresponding vector space. And the trick is that when you why this you need why this so the exactly why the Whitney trick works, because here one point is taken with positive orientation and one point is taken with negative orientation. So you may think that it is bad, yes, so because this when you go along this loop and along this loop, the orientations will be inconsistent, yeah? So you are just moving from the other side, and the orientation of this complementary vector space Tp and Tq that you have taken for trivialization is inconsistent with this kind of trivialization. But the trick is that when you are moving along why this Whitney trick works, because you are taking not the bundle Tp but orthocomplement. And the orthocomplement it is taken to this tangent vector to the curve. And when you are taking this orthocomplement, yeah, so there is another tangent vector. So this here you have a tangent vector to this curve, yeah? So you have this curve and this one. So this part of the curve. And here you have the corresponding tangent vector to GQ. And the matching is done that this TP, this one, and the tangent space of Q gives you the basis. But when you move to this part, you change so the direction of. So the trick is that this TP is not changed, but the vector that you have constructed. So the vectors that are skipped, so they are interchanged, are the vectors along which is. So this tangent vector becomes normal and vice versa. Yeah? So in this, when you have this angle, this tangent vector becomes normal to this curve, and this normal vector becomes tangent to the curve. So you have to interchange them when you are picking up the corresponding, writing down everything in terms of complements, and sweeping precisely this vector says that you can, you should change the orientation in these 2 points. So this element of the fundamental group cancels. So this is more or less Whitney trick. So maybe it is a good point to stop here. Ладно.
Включить запись.